We all know that one day, Earth won't remain habitable forever. History has already shown us the warning signs. Asteroids have struck before, wiping out nearly 99% of life during the age of the dinosaurs. Then came the Ice Ages, where once again much of life disappeared. These events remind us that extinction is not a distant theory. It has happened, and it could happen again. And not every catastrophe takes millions or billions of years to unfold. The sun, our life-giving star, also holds the power to destroy us. If it swells into a red giant, Earth would overheat, oceans would boil away, and the atmosphere could vanish. If it dims, the planet could freeze into a lifeless world of ice. Thankfully, those transformations lie billions of years in the future, but the fact remains, they are inevitable. But there are faster, more pressing dangers. Every 11 years, the sun releases solar flares, violent bursts of energy that can damage Earth's atmosphere. If one is strong enough, it could weaken our protective shield and allow vital gases like oxygen and water vapor to escape into space, leaving behind a dry and lifeless planet. Our defense against this threat is the magnetosphere, Earth's invisible shield that deflects harmful solar particles. Yet this shield is not permanent. Throughout geological time, the magnetic poles have reversed again and again. If a powerful solar storm strikes during one of these reversals, the magnetosphere could fail, and the surface might become uninhabitable within years, not millennia. Mars shows us what such a fate looks like. Billions of years ago, it had rivers, lakes, perhaps even oceans. But once its atmosphere was stripped away by solar winds, it became the barren world we see today. Earth faces the same risk, though so far, our magnetic field has held strong. So if the surface becomes unlivable, how do we survive? Space colonization is often imagined, but in reality, it is not an option for billions of people. Life on Mars or any other planet would be harsh, uncertain, and unsustainable. Instead, scientists and researchers point to a far more practical solution: underground colonization. By moving 10 to 12 kilometers beneath Earth's surface, humanity could shield itself from radiation, solar storms, and extreme atmospheric collapse. The challenges are immense. At such depths, temperatures can reach 390 to 570 degrees Fahrenheit, enough to melt rocks and metals. How would we survive the heat? Where would our oxygen and water come from? And how would food grow without sunlight? It may sound like science fiction, but modern science and technology are already making it possible. This chapter explores exactly how underground civilizations could function, how people could breathe, eat, and thrive beneath the Earth when the surface above is no longer safe. As we consider the possibility of life continuing deep underground, attention naturally turns to the hidden potential beneath the Earth's surface. It's a realm largely unexplored, where heat, minerals, and energy flow in patterns largely untouched by human hands. Understanding how to harness these natural forces and how life might adapt to them becomes the first step in imagining a civilization that could endure long after the surface is no longer hospitable. This underground world is not just a theoretical idea. The Earth itself provides everything we would need to survive, if only we can access it. At the heart of this hidden sanctuary is the planet's core, an immense reservoir of heat and energy that has remained molten and active for billions of years. Temperatures at the core reach levels almost comparable to the surface of the Sun, a staggering 5,500 degrees Celsius. Yet the Earth's layers above insulate this heat, releasing it only slowly. At the very surface, the planet loses energy at a minuscule rate of about 100 milliwatts per square meter, a tiny trickle when compared to the vast heat stored deep within. This slow leakage means the core's energy could continue to flow for billions of years, potentially outlasting the sun itself. Understanding this heat source is crucial because it transforms the concept of underground living from fantasy into a feasible possibility. The energy stored in the Earth's interior could power homes, provide warmth, and even generate electricity for ventilation, lighting, and other essential systems. In a world where sunlight is no longer a given, the Earth becomes both protector and provider, replacing the familiar cycles of day and night with a new, reliable source of life-sustaining energy. But why is the Earth's core still so hot, especially when we know other planets like Mars have long since cooled? The answer lies in a combination of insulation, radioactive decay, and tectonic activity. Earth's outer crust acts like a natural blanket, slowing the escape of heat in much the same way a thermos keeps water hot for hours. Deep inside, radioactive isotopes, primarily uranium, thorium, and potassium, continuously decay, releasing heat and replenishing the core's energy. On top of that, the slow movement of tectonic plates generates friction, adding more heat to the interior. Together, these factors create a self-sustaining system, ensuring that Earth's core remains molten and active, while smaller, less dynamic planets gradually lose their internal heat. With the presence of this hidden energy, the next question is, where exactly could humans build underground settlements? Scientists have identified regions known as geothermal stability zones, layers deep beneath the surface where conditions remain remarkably consistent. Typically located between 10 and 15 kilometers underground, these zones feature temperatures ranging from 200 to 300 degrees Celsius, solid rock formations, and a low risk of earthquakes. In essence, they offer stable and secure environments, capable of sheltering large populations safely away from the hazards of the surface. It's natural to wonder why we would need to go so deep. After all, just 10 meters of soil can block most harmful solar radiation. The answer lies not just in protection, but in space, resources, and long-term sustainability. Shallow shelters are limited. They can provide safety for a small number of people for a short period, but they cannot support an entire city or complex civilization. By venturing deeper, we unlock the ability to build extensive underground networks, harness geothermal energy efficiently, and create living spaces that can support communities for decades or even centuries. The deeper zones provide more than mere survival. They offer the possibility of a self-sustaining civilization, insulated from surface threats, yet thriving with access to heat, power, and structural stability. Scientific research supports this vision. Dr. David Guberman, the pioneering geologist behind the Kola Super Deep borehole, drilled nearly 12 kilometers into the Earth, exploring the properties of deep rock layers. His findings revealed solid, stable formations at extreme depths, demonstrating that these layers could serve as a foundation for human habitats if properly engineered. Following Dr. Guberman's work, NASA and MIT confirmed the potential of geothermal stability zones, verifying that these layers could be safe, predictable, and suitable for large-scale underground construction. For every kilometer descended, the temperature rises about 25 to 30 degrees Celsius, meaning that at 10 kilometers deep, temperatures would reach a manageable 200 to 300 degrees Celsius, a level that can be addressed with advanced cooling and engineering systems. Harnessing the Earth's heat is not just theoretical. Geothermal energy systems can convert this internal warmth into electricity, heating, and ventilation for underground habitats. Unlike solar or wind power, which can fluctuate and sometimes fail, geothermal energy is constant and reliable, providing a steady supply of power regardless of surface conditions. Using turbines, heat exchangers, and circulation systems, an underground city could operate continuously, day and night, without dependence on the sun or external fuel sources. In other words, the Earth itself becomes a living power plant, capable of supporting life far below the surface. Yet reaching these deep layers is no trivial matter. Traditional drilling methods struggle beyond 5 or 6 kilometers because of extreme heat and pressure. Drill bits can melt, warp, or break, halting progress and making precision impossible. To overcome these challenges, engineers have developed plasma drilling, a technique that melts rock without physical contact, creating tunnels safely even under extreme conditions. MIT has also created laser drilling systems, which cut through rock at speeds 15 times faster than conventional drills, opening up previously unreachable depths for construction. Robotic technology further enhances the feasibility of underground habitation. NASA's concept of robotic autonomous swarms involves coordinated groups of small machines working much like ants in a colony to dig tunnels, transport materials, and construct habitats. These robots can perform delicate tasks in extreme conditions, building underground cities efficiently while keeping humans out of harm's way. The combination of plasma, laser, and robotic systems makes it possible to access and shape deep Earth zones that were once beyond human reach. Once access is secured, the question of construction arises. What materials will we use to build these subterranean homes? Fortunately, the Earth provides its own resources. Rock can be cut, fused, or melted to form walls, tunnels, and domes. Molten rock can be recast into structural materials, forming strong, heat-resistant chambers. In addition, lightweight inflatable modules can be sent from the surface, deployed underground, and expanded within stable rock layers to create habitable spaces. This hybrid approach, combining natural and engineered materials, allows for safe, flexible, and durable structures capable of housing large populations. Existing projects demonstrate that underground habitation is not mere theory. The Neutrino Laboratory, located 1.5 kilometers beneath the surface, operates in controlled, stable conditions, providing proof that humans can work and live safely underground. These examples reveal that underground survival is already possible in limited forms, offering a blueprint for scaling up to larger, more comprehensive settlements. Now, we've seen how underground habitats could be built and how people might actually live there, but let's be honest, there's one huge burning question left. How on earth do we deal with the heat? I mean, the rock around us down there isn't just a little warm. It's hot enough to roast a pizza in seconds. Temperatures between 200 and 300 degrees Celsius can turn even the strongest structure into a blazing oven. So, the first step in making these deep underground homes livable is figuring out how to cool them down without turning life into a nightmare. Here's the interesting part. The answer already exists, and we can learn it from some of the craziest science experiments humans have ever done. Take the Large Hadron Collider at CERN in Europe, for example. This massive particle accelerator sits underground in tunnels, not all that different from the stable rock layers we've been talking about. But inside those tunnels, scientists need to keep parts of it at nearly minus 273 degrees Celsius, which is almost absolute zero. Why? Because the superconducting magnets used to guide tiny particles absolutely cannot heat up. They need to stay icy cold to work perfectly. To pull this off, CERN uses liquid helium, which absorbs the heat from the magnets and keeps everything running smoothly. You might be thinking, cool, but what does particle smashing have to do with underground homes? Well, it turns out quite a lot. The same principle can be applied to our underground colonies. Instead of letting the heat of the Earth roast our tunnels, we can install pipes inside walls or floors and circulate cooled liquids or synthetic fluids through them. These fluids act like a giant sponge, sucking the heat out of our living spaces. The rock around us is still hot, but inside the habitat, it stays comfortable and safe for people. In other words, the heat that once seemed like a threat becomes something we can control and even use. So, now that the heat is absorbed by the fluid, what happens to it? It doesn't just disappear. In fact, this is where the system gets really clever. At CERN, the heat absorbed by liquid helium is transferred to a heat exchanger, which then passes the energy to water. That water can then be sent through insulated pipelines to nearby cities, where it can actually warm buildings, schools, or offices during cold months. Imagine that. The heat that could have killed us underground becomes a free, useful energy source for the world above. For our underground cities, a similar setup could be scaled up. The heated fluid could be turned into steam, which drives turbines to generate electricity. That electricity can then power air conditioning and other systems to keep the colony comfortable. The best part? This could run continuously without stopping, cycling heat from the walls into the fluid, through turbines, and back into the system. The colony becomes almost like a living, breathing machine, powered by the Earth itself. And it doesn't stop there. There are already large-scale cryogenic systems and industrial coolers that handle extreme temperatures every day, from labs to manufacturing plants. We can borrow those ideas, tweak them for underground living, and suddenly, spaces that would have been uninhabitable due to heat become perfectly livable. The combination of cooling fluids, turbines, and smart piping creates a self-sufficient climate system that works automatically. Another cool thing about this method is how energy efficient it is. Since the heat is already there, we don't need extra fuel or electricity to power the cooling. In fact, by turning that captured heat into electricity, the colony could even generate more energy than it consumes for cooling. It's a sustainable loop. Earth gives us heat, we capture it, and it powers the very systems that keep us alive and comfortable. Flexibility is another major win. Different areas underground will have slightly different temperatures. Engineers could tweak the cooling loops depending on the depth and how hot the rock is. Some sections might need minimal cooling, while others could use more intensive fluid circulation or extra heat exchangers. And it's not just a single building. We could have a network of pipelines, turbines, and cooling stations, all working together like a giant circulatory system for an entire underground city. Safety is built right in. Autonomous systems would constantly monitor temperatures, fluid flows, and turbine performance. If something goes wrong, backup systems kick in automatically. In this setup, people could focus on living, working, and exploring, while the mechanical system quietly handles the intense heat all the time. Over time, these could become fully automated habitats, running themselves with minimal human intervention, keeping the colony perfectly comfortable all the time. This heat management also opens doors for some incredible underground city designs. With the temperature problem solved, architects could build multi-level colonies, complete with living quarters, offices, schools, labs, and even recreation spaces. The heat of the rock is no longer a problem. It becomes part of the design, feeding turbines, insulating rooms, and helping regulate the ecosystem underground. Ultimately, what seems like a huge challenge, living in rock-heated spaces, is actually an opportunity for innovation. By taking cues from particle physics labs, cryogenic systems, and industrial engineering, humans could turn a dangerous environment into a comfortable, self-sustaining habitat. The heat that once threatened life now powers the colony and helps maintain a livable climate, creating a self-regulating ecosystem where energy and temperature work in perfect harmony. So, underground living isn't just about survival, it's about human ingenuity at its finest. It's about working with the earth, harnessing its energy, and creating cities that can thrive even in complete darkness. By mastering heat management, we set the stage for everything else: food, water, air, and the full infrastructure of life underground. The solutions to this intense heat hint at a bigger picture: a fully self-sufficient underground civilization, able to withstand anything the surface world throws at it. And with that solved, the next question naturally comes up. How do we provide food, water, and breathable air in these deep underground homes? The heat solution is just the beginning. It shows us that, with the right systems, humans could thrive below the surface. What follows is a complete underground ecosystem, where life adapts to the Earth's interior rather than relying on the sun, and where ingenuity turns extreme conditions into opportunities for survival and growth. The first thing we need underground is simple: air. Without oxygen, no amount of technology, food, or shelter matters. But if you think about it, we've already solved this problem in some of the most extreme environments imaginable. For more than 2 decades, astronauts aboard the International Space Station have lived without ever opening a window. Their oxygen doesn't come from outside, it's made inside. Special machines split water into hydrogen and oxygen through a process called electrolysis. The oxygen is breathed in and the hydrogen is vented out into space. If we can run these systems in orbit, where resupply missions are costly and dangerous, then surely we can adapt them for life beneath the Earth. And it doesn't stop there. Technology is already getting smaller, cheaper, and more portable. Honda has developed a compact oxygen generator capable of producing enough breathable air for 3 astronauts continuously. Imagine scaled-up versions of such systems forming the lungs of an underground city, humming quietly in the background, ensuring every resident has clean, breathable air. But oxygen generation isn't only about fancy machines. Submarines, for example, have long produced oxygen for crews living underwater for months at a time. They use chemical processes that can strip oxygen from water or scrub carbon dioxide from the air and recycle it. These aren't just concepts, they're proven technologies operating daily under the sea. If we can breathe safely in a steel tube hundreds of meters below the ocean, we can certainly do it inside massive underground caverns carved out by humanity. The second challenge is water. At first, this feels like a bigger problem. No rain, no rivers, no lakes deep underground. But again, nature and technology already point us towards solutions. Take Israel, for instance. In arid deserts where rainfall is rare, companies have pioneered machines that literally pull water out of thin air. One device, called WaterGen, can produce a liter of drinking water every hour using about 1 kilowatt of energy. Armies and disaster relief agencies already use it in places where wells have run dry. Underground, such machines could be a lifeline, turning humidity from ventilation systems into fresh, drinkable water. And nature offers another option: aquifers. These are hidden pockets of water trapped deep within the earth. Research by the United States Geological Survey has revealed that aquifers can exist even 10 to 15 kilometers below the surface, the same depths we're imagining for underground colonies. Humanity already drills kilometers into the earth to reach oil, gas, and geothermal energy. Extracting water is not only possible, it's something we've mastered. So between atmospheric water generators and deep aquifer tapping, underground settlers would have not just drops, but streams of water flowing into their new world. With air and water secured, the third element is food. And here's where things get fascinating. On the surface, farming depends on sunlight, soil, and open fields. Underground, we obviously lose those. But the question isn't, can we farm without them? It's, how do we replace them? The answer is already here: vertical farming. Instead of sprawling fields, plants are grown in stacked layers, each carefully lit by LED panels. These aren't ordinary bulbs, but full-spectrum lights tuned to mimic the sun's energy. Plants don't care if the photons come from a distant star or a diode. They'll photosynthesize either way. Using aeroponics and hydroponics, crops can grow without soil, suspended in nutrient-rich water or mist. But it's not just about stacking plants in layers. Temperature, humidity, and nutrient concentration are all tightly controlled. Sensors monitor each plant in real time, adjusting conditions to maximize growth. Artificial intelligence can predict when a plant will need more nutrients or water, and robotic arms can prune or harvest crops efficiently. In effect, underground farms aren't passive. They're active, intelligent ecosystems designed for maximum yield and minimal waste. The results are extraordinary. Such systems use a fraction of the water traditional farming consumes. Plants grow nearly twice as fast. There's no risk of soil-borne diseases. And because everything happens in a controlled environment, yields are stable and predictable. Imagine entire underground towers of greenery: lettuce, spinach, tomatoes, cucumbers, all thriving in the glow of artificial sunlight. Even delicate crops like berries or microgreens, which are notoriously hard to cultivate outdoors, can flourish here. Protein, of course, is essential. Underground settlers won't survive on salad alone. But again, solutions exist. Mushrooms, rich in protein, can be cultivated easily in low-light, humid environments. Fungal protein, known as mycoprotein, is already used in food products on Earth today. Add to this lab-grown meat, cultured in bioreactors rather than on farms, and suddenly the underground menu doesn't seem so limited. Fish, chicken, even beef can be produced in these bioreactors with minimal space and water. offering a complete nutritional profile. Beyond plants and protein, there's an opportunity to grow essential vitamins and medicinal plants. Herbs like basil, mint, and aloe vera can be cultivated to provide natural supplements. Even more ambitious, algae such as spirulina can be grown in photobioreactors, supplying a dense source of nutrients while taking up very little space. These systems could turn the underground colonies into nutrient-rich powerhouses, capable of feeding thousands without relying on the sun at all. Still, long-term resilience demands more than just growing today's crops. We'd need to preserve biodiversity. That's where seed banks come in, vaults storing the genetic blueprints of plants from around the world. One already exists in Svalbard, Norway, where millions of seeds are kept in frozen storage inside a mountain. An underground civilization could maintain its own vault, ensuring that if Earth's surface ever becomes habitable again, humanity can replant, regrow, and restore. But more than preservation, such a bank could be a source of experimentation, allowing settlers to cultivate new varieties adapted specifically to underground conditions, selecting crops that thrive under artificial lighting, limited space, and controlled humidity. And it's not just plants. Fungi, algae, and even insects can become part of a balanced underground diet. Cricket protein, for instance, is highly sustainable and requires minimal resources to raise. Certain edible larvae could provide additional nutrition, forming part of a self-contained food web. By combining these unconventional sources, the underground settlers could maintain a diverse, balanced diet that supports health and energy for years, even decades. All of this paints an amazing picture. Oxygen made from water, water pulled from rock or air, and food grown under LEDs in stacked towers. But more than the technology, it's the vision that matters. Because what seems impossible, living without the sun, actually becomes practical when you combine these systems into one self-sustaining cycle. Picture it: giant caverns glowing with artificial daylight, filled with rows of green crops. Nearby, humming machines split water into oxygen. Underground rivers feed hydroponic tanks. Families breathe clean air, drink pure water, and eat fresh food, all while the surface world above lies scorched or frozen. And perhaps most remarkable of all, it's not pure science fiction. Every piece of this puzzle exists today, in some form. The challenge is integration, scaling these technologies, combining them, and adapting them to the extreme environment beneath our feet. So if the sun ever turns hostile, or if Earth's shield fails, humanity won't necessarily have to flee to Mars or another star. We may only need to look downward into the planet that gave us life and build a new kind of civilization in the depths. As we imagine these vast underground cities, glowing with artificial daylight, stocked with fresh food and flowing water, and humming with the clean air produced by human ingenuity, it's easy to feel a sense of relief. For a moment, it seems as if we've solved the impossible. Oxygen, water, food, all secured. But before we start celebrating, there's another, less obvious threat lying in wait beneath our feet. One that doesn't come from the sun, the atmosphere, or even from running out of resources. It comes from the very Earth itself, the restless, shifting tectonic plates. The ground beneath us may feel solid, unyielding, even eternal. But Earth is alive. Its crust floats on a convective layer of molten rock, and its enormous slabs, tectonic plates, are constantly moving, albeit slowly. They collide, grind past each other, and sometimes lift or sink regions of the planet. This slow dance has shaped mountains, carved valleys, and caused earthquakes throughout history. On the surface, we adapt. Buildings are reinforced, cities have emergency plans, and earthquake zones are mapped. But deep underground, where entire colonies might lie, a shifting plate could be catastrophic. A quake, a sudden tremor, or even the slow movement of stress along a fault line could crush tunnels, fracture water channels, and collapse entire living areas in seconds. So the question becomes, how do you design an underground civilization that can survive the raw, unpredictable power of Earth itself? How do you ensure that every underground farm, every oxygen generator, every family is safe when the planet's crust beneath them decides to move? Engineers and geologists approach this challenge in two complementary ways: site selection and active safety systems. First, site selection. Not all parts of the Earth are equally dangerous. In fact, there are regions where the crust has remained remarkably stable for hundreds of millions of years. These ancient geological formations, called cratons, are essentially the bedrock of stability. They have experienced little tectonic movement, sometimes for over 3.5 billion years. Building deep underground in these zones dramatically reduces the risk of earthquakes or destructive plate shifts. Examples include the Canadian Shield, the Indian Peninsular Shield, and the Australian Craton. In India, for instance, Karnataka and Telangana sit atop such stable layers. Choosing such locations isn't just convenient, it's the first line of defense. It's as if nature herself has created safe zones for humanity to retreat beneath the surface. But what about the rest of the world? Not every country is blessed with cratons. Much of the globe sits atop active plate boundaries, where the ground can shake violently, and earthquakes or volcanic activity are part of regular geological life. If underground colonies were constructed in these areas, additional layers of engineering protection become crucial. This brings us to active monitoring systems. Modern engineering allows us to equip underground settlements with highly sensitive stress and vibration sensors. These aren't your typical alarms. Embedded throughout the rock surrounding tunnels and living spaces, they can detect minuscule shifts or pressure changes long before humans can feel them. A faint microfracture? Detected. Slight vibration indicating tectonic movement? Detected. Once these sensors pick up unusual stress, they instantly communicate with the colony's central safety system. Doors seal, structural reinforcements are activated, and residents are guided to safe zones, all automatically. Some of this technology already exists in places like the Gotthard Base Tunnel in Switzerland. Engineers there monitor pressure and vibration continuously, ensuring that the tunnels remain safe under the immense weight of the Alps above. These systems are scaled for human survival in real time. Imagine expanding this to an entire underground city, kilometers deep. Every street, every corridor, every cavern network monitored constantly for signs of danger. But detection is only one part. The next challenge is mitigation. Even in stable areas, earthquakes can still occur, and fractures may appear. To counter this, engineers are developing autonomous life support chambers. Think of them as the underground equivalent of the International Space Station or a submarine's safety pods. If a quake blocks the main tunnels or compromises a colony section, these chambers can seal themselves automatically. Inside, they contain enough oxygen, food, and water to support residents for several days, giving rescue teams the time they need to reach them. It's a simple yet revolutionary idea. Even if part of the colony is damaged, the inhabitants remain safe. Rescue infrastructure also takes inspiration from natural designs. Just as moles create multiple tunnels to escape predators, underground colonies can be planned with vertical rescue shafts, numerous exit points that connect the main caverns to the surface. These aren't just emergency stairwells, they're high-tech lifelines. Using 3D imaging, ground-penetrating radar, and LiDAR scanning, rescue teams can map blocked or unstable tunnels, calculate the safest path to trapped individuals, and send supplies if needed. Historical examples, like the 2010 Chilean mine rescue, demonstrate how well-planned access shafts and technology can save lives even hundreds of meters underground. 33 miners survived 69 days trapped, thanks to a combination of planning, communication, and specialized rescue shafts. The lessons are clear. In a deep underground civilization, a network of escape routes isn't optional, it's a survival necessity. Material choice also matters. The tunnels and chambers of the future won't just be carved rock. Engineers can integrate flexible materials and damping layers into walls to absorb seismic shocks. Reinforced composite materials, coupled with active support beams, can allow tunnels to bend slightly rather than fracture. Even certain types of concrete, when combined with steel lattices, have been proven to withstand strong vibrations without collapsing. Every inch of construction underground can be designed not just to withstand pressure, but to move with it. Energy systems, too, need protection. Underground cities rely on electricity to run air circulation, hydroponic farms, water pumps, and life support systems. Earthquakes can damage power lines or generators, so colonies would incorporate redundant energy sources. Backup batteries, isolated solar arrays on the surface protected from weather extremes, and even geothermal generators that harness the heat of the Earth itself. By creating multiple independent energy loops, the city ensures that even if one system fails during a quake, essential life support continues. Interestingly, tectonic movement doesn't always have to be purely destructive. The same geothermal energy generated by plate interactions can become a source of power. Heat from the Earth's interior, accessed safely, can run turbines, warm water, and even support underground agriculture. In a way, the planet's raw power, if understood and managed, becomes a partner rather than just a threat. Planning goes even further than the physical structures. Colonies must incorporate emergency protocols and AI-assisted management systems. Artificial intelligence can monitor every sensor, predict potential hazards, and even simulate what-if scenarios for various earthquake magnitudes. Residents may be guided by digital displays or audio instructions to move to reinforced chambers, where structural stress is minimal. AI can also coordinate rescue robots, drones, and autonomous vehicles to reach trapped individuals faster than any human responder could. Finally, long-term underground survival requires thinking beyond a single quake. Repeated seismic activity could gradually shift water channels, destabilize farms, or weaken structural supports. Engineers anticipate this by designing modular, replaceable structures. Sections of tunnels or farms can be detached and moved, while support scaffolds can be reinforced incrementally. The city is alive, evolving, and adapting to the dynamic environment in which it exists. All of these strategies combine to answer one vital question: can we truly make life underground safe from the Earth's own forces? The answer is cautiously optimistic. With careful site selection, advanced monitoring, resilient materials, autonomous safety chambers, vertical rescue shafts, and adaptive infrastructure, the dream of a fully functional underground civilization moves closer to reality. We're not just hiding from the sun or preserving water and oxygen, we're learning to dance with the planet itself, to turn its dangerous energy into both a challenge and a resource. So, the picture emerges. We've secured air, water, and food. Now, we confront the next danger: the shifting, unpredictable crust of the Earth. It's a test of human ingenuity on a grand scale. And as we imagine these tunnels and caverns, humming with life and lit by artificial daylight, we realize that survival underground isn't just a matter of science. It's a combination of geology, engineering, AI, and strategy, all working together to protect life in the heart of a restless planet. By preparing for tectonic movement in advance, designing systems that can withstand, adapt, and even utilize the Earth's inner power, humanity transforms underground colonies from a fragile experiment into a robust, self-sustaining civilization. It's a bold step, a journey into the depths where danger lurks, but opportunity thrives. And as we move further into this exploration, it becomes clear that surviving beneath the surface is less about escaping the world above and more about mastering the world below. But once the foundations of survival are in place, a deeper challenge emerges, one that no sensor, pump, or reactor can fully solve. If people move permanently beneath the Earth's crust, the question shifts from how do we survive to how do we live as human societies. A civilization is more than oxygen and food. It is culture, identity, relationships, and systems of order. And in the silence of rock-hewn caverns, where no horizon or sky exists, those elements would have to evolve into something new. At first, life underground might feel like an emergency shelter stretched into permanence. Shared air systems, shared water cycles, shared farms. Privacy would be limited, and individuality pressed against the demands of collective survival. But humans are builders of worlds, not just maintainers of them. Inevitably, questions would arise. Who controls the farms? Who owns the energy systems? What happens when one colony has more geothermal power than another? Does trade exist underground, or does survival erase the very idea of markets? The old blueprint of nations carved across continents would no longer apply. Borders, after all, depend on open land, on rivers and mountains and skies. In tunnels and chambers, space is finite and carved by machines, not geography. Instead of countries, humanity might fracture into city-states of stone, each colony a self-contained world, lit by its own artificial day, powered by its own reactors, and governed by its own rules. Cooperation would be essential, but so would independence. And here, a strange paradox appears. On the surface, nations compete for land and resources. Underground, the most precious resource is space itself. Who decides how deep to dig, how wide to carve? Does one colony own the caverns it creates, or is everything beneath Earth's crust a shared human domain? Economy, too, would bend under these pressures. Currency, in its current form, relies on the abstract flow of markets. But in the depths, value becomes physical again. A liter of clean water, a kilowatt of energy, a single cubic meter of breathable air. Instead of dollars or digital coins, underground life might be measured in credits of survival. Every breath linked to the energy grid, every meal tied to the cycle of crops in vertical farms. Imagine an economy where electricity is not just a utility, but the backbone of wealth itself. Jobs, too, would transform. Traditional roles tied to sunlight, farming, construction, transport, would shrink, while new roles expand. Hydroponic engineers, bioreactor technicians, atmosphere regulators, rock stability monitors, entire professions born from the act of living beneath stone, and over time, these roles would shape identity. A child born underground might see an oxygen systems manager the way a child on the surface once saw a farmer, as the foundation of life itself. Yet survival does not erase ambition. Even in enclosed worlds, culture would bloom. Art would adapt to cavern walls. Music would carry differently in tunnels, echoing in haunting ways. Festivals might revolve around artificial dawns and dusks, programmed by light cycles. And though no stars shine underground, perhaps humanity would paint constellations on ceilings, reminders of the sky once lost. But would people stay unified? Or would rivalries grow sharper in the dark? One colony with abundant geothermal energy might thrive, while another, trapped in weaker rock, struggles. Do they share? Do they compete? History suggests cooperation only lasts until scarcity appears. And underground, scarcity is the rule. This opens a haunting possibility: underground wars. Not fought with armies under open skies, but with sabotage of air ducts, hacking of power grids, or blockades of tunnel routes. A civilization compressed into stone would face pressures as much social as physical. Peace might demand stronger systems than humanity has ever built before. Perhaps AI-managed distribution of resources, impartial and unbribable. But that raises new dilemmas. Do humans surrender control to algorithms, trusting machines to allocate every drop of water, every breath of air? The deeper the thought runs, the more it reveals how alien underground life could become. Imagine generations born with no memory of sunlight. To them, surface Earth might feel like myth, as distant as Atlantis or Eden feels to us. Their sense of time shaped not by sunrises, but by clockwork shifts of artificial light. Their sense of space compressed to tunnels and caverns, with no horizon to dream toward. Would such people still call themselves Earthlings? Or would they adopt new identities, caverners, subterrans, children of the depths? Over centuries, cultural evolution might split humanity into two: the descendants of those who stayed on the surface, struggling against solar storms or rebuilding in safe pockets, and those who disappeared underground, adapting to a life divorced from sky and soil. And what of governance? On the surface, nations are vast, populations are spread, and power often lies distant from daily life. Underground, governance would be intimate. A leader's decision about energy allocation could be felt instantly in every household's air quality. Democracy might shrink into direct participation or grow into technocracy where only engineers and scientists can decide the future. Either path changes what it means to be governed and to belong. Then there is the question of expansion. Once the first colonies thrive, do they dig further, deeper, spreading like roots through the planet's crust? Imagine networks of tunnels connecting continents, underground highways glowing with bioluminescent light, cavern cities linked like nodes in a web. Earth could transform into a planet of two faces, a scorched or frozen surface above, and a hidden lattice of civilizations below. And still, with all this, one question lingers. What does it mean to thrive without the sky? Can humanity, a species born under stars, truly adapt to life without ever seeing them again? Or would there always remain a pull, a longing for open horizons? Perhaps underground life is not the end of humanity's story, but a pause, a cocoon from which something new emerges, something waiting for the day the surface becomes kind again. The future underground, then, is both promise and puzzle. We can map the engineering, chart the geology, even design the farms and reactors. But what cannot be calculated are the choices: how we live together, how we govern, how we dream. Technology builds the shelter. Culture decides what happens inside it. And so, the vision of underground life remains unfinished. It is not a neat ending, but an open horizon, turned inward instead of upward. A horizon carved into stone, lit by human hands, waiting to reveal what kind of society we dare to build when the sky is no longer ours. So, what we've explored in this video shows that underground life isn't just a distant idea, it's a real possibility. Scientists and engineers have already mapped out how to secure air, water, food, and safety in the depths beneath our feet. From oxygen generation to vertical farming, from water extraction to heat management, each system is grounded in research and technology that exists today. The vision of a fully functional underground civilization is no longer science fiction. It's a blueprint being refined for the future. Yet, even with these solutions, many questions remain unanswered. How will these subterranean networks grow over decades? How will humans adapt culturally, socially, and psychologically to life far from the surface world we've always known? These are challenges that time, innovation, and human ingenuity will reveal. For now, survival comes first. Creating a secure, thriving environment beneath the earth is the essential first step. And while the timeline is uncertain, the foundations are already being laid. The moment may come when humanity turns downwards, transforming the Earth's interior into a refuge against a harsh surface. Until then, we watch, learn, and prepare. If this journey beneath the Earth sparked your curiosity, make sure to like this video, share it with others who wonder about the future of humanity, and subscribe to explore more insights and discoveries waiting just below the surface.